Hello all. Today we'll discuss our final chapter of the course, Chapter 23, The Sun, the Stars, and Deep Space. This chapter could be divided up into a discussion of our Sun and its characteristics, then a discussion of stars and stellar evolution in general, and finally a discussion of the different galaxies and structure of the universe as a whole. Our Sun is a relatively small star and is fairly ordinary. When we study it up close, we use our understanding as a basis to study other stars. Our Sun is composed of 71% hydrogen, 21% helium, traces of many other elements, and of plasma, which is a state of matter that includes ionized hydrogen and helium atoms circulating with free electrons. The source of the Sun's energy comes from nuclear fusion. In the Sun, this series of reactions fuses 4 hydrogen atoms to form 1 helium atom. The difference in mass from start to finish has been converted into energy, and this is referred to as the proton-proton chain. So in the figure below, you start with 2 separate sets of 2 hydrogen nuclei, or protons. In each set, the same reaction occurs, where the 2 hydrogen protons combine, releasing a positron, a neutrino, and a gamma ray. That results in 1 proton and 1 neutron, and the isotope 2 hydrogen. When another proton is added to this, we get the isotope 3 helium, which has 2 protons and 1 neutron. Then that 3 helium combines with another 3 helium, which knocks off 2 protons and produces 4 helium with 2 protons and 2 neutrons. Here is a picture of the internal structure of the Sun. Like the Earth, the interior of the Sun is differentiated. Although in the Sun, composition doesn't really change. It's only differentiated by temperature and pressure. The main layers are its core, its radiative zone, and its convective zone, shown in the figure below. Solar granulation results at the Sun's surface, shown in photographs, where hot plasma is sinking and rising. Hot rising material appears light, whereas cooler sinking material appears darker. We have a view of the whole Sun, as well as a close-up view and a schematic to scale. The solar atmosphere can be divided into the photosphere, which is the visible surface of the Sun, the chromosphere, which is the thin bright band surrounding the Sun and is visible during the eclipse, and finally the corona, which is the outer layer of the solar atmosphere. The photosphere is the layer at which we measure the characteristic temperature of the Sun as a star. The chromosphere is a thin layer of hot gases above the photosphere, and it is red in appearance and can only be seen during an eclipse or through special filters, shown in the figure below. The corona is the outer layer of the solar atmosphere, which extends several times the diameter of the Sun. On the left is the inner part of the corona just above the chromosphere, and on the right is the outer part of the corona. In each case, portions of the Sun or its atmosphere are blacked out to show the contrast. The solar wind is a high-speed stream of particles, mostly protons and electrons, that escape from the Sun's gravity. Moving matter, not just energy, these particles travel at 500 kilometers per second. The Earth's magnetosphere deflects most of these electrically charged particles, although particles that stream down towards the surface at Earth's poles produce the aurorae. The sun's magnetic field is produced by rapid circulation of the plasma within the convective zone, because plasma is an electrical conductor. It is complicated because solar rotation varies with latitude. This warps the magnetic field lines over time. So here we can see faster rotation at the equator and changing of the magnetic field lines as a result. Sunspots are patches on the sun's surface that have cooled as upwelling plasma has been inhibited by strong magnetic fields that arc out of the surface. These always occur in pairs where the field exists and then where the field exits and then re-enters the surface. As field lines become more warped over time, the solar magnetic field eventually collapses and then reforms. Sunspot numbers increase as lines become more warped, then drop off sharply. This occurs over an 11-year period known as the sunspot cycle. Solar prominences are outbursts of glowing glass and plasma emerging from the sun's surface that follow magnetic field lines back to the surface. Flares are even brighter eruptions of plasma that shoot out of the sun's surface and release a huge amount of energy, as well as X-ray and UV rays. Material ejected from prominences and flares contribute to the solar wind. Space weather is a recently coined term that describes conditions on Earth caused by particles coming from the sun, or the solar wind. Some effects are the disruption of satellite systems, hobbling communication systems, damage to electrical grids, disruptions to cell phones, or affecting GPS navigation. Now let's discuss stars in general and stellar evolution. Stars vary in brightness not only depending on how far they are from Earth, but depending on their composition and the stage that they are in their evolution. Variation in brightnesses occur as a result of luminosity, which is the amount of electromagnetic energy emitted in a specified amount of time, and apparent brightness, which is the amount of energy from a star that passes through a square meter at the surface of the Earth in 1 second. So these are absolute and apparent or relative measurements. Apparent magnitude is the classification of a star's brightness as seen from the Earth, and absolute magnitude is a star's brightness magnitude if it were a distance of exactly 33 light years or 10 parsecs from the Earth. This removes the effective distance to the object. Below is a figure of apparent versus absolute magnitudes for nearby stars relative to the observer on Earth. The temperature of a star is indicated by its color, and astronomers divide stars into spectral classes based on their temperatures. Spectral classes are O, B, A, F, G, K, and M, going from highest surface temperature to lowest surface temperature. Note that colors are blue for the highest temperature stellar surfaces, white and yellow for middle temperature, and orange to red for lowest temperature. Stars also vary in size from dwarfs to supergiants. Their size is related to other characteristics like composition, temperature, and stage in evolution. So here's our sun relative to other stars like Canopus, Rigel, and Betelgeuse, among others. The Hertzsprung-Russell diagram is a graph with surface temperatures plotted on the x-axis relative to luminosity plotted on the y-axis. As you can see, stars do not fall randomly on this diagram, but fall into certain groups. Most stars, including our sun, lie in a narrow band that goes from the top left of the diagram to the bottom right of the diagram, or highly luminous, high temperature, to low luminosity, low temperature, This band is called the main sequence. In addition to the main sequence, there are portions of this diagram that show where the white dwarf stars exist, where subgiants, giants, bright giants, and supergiants exist. Notably, although this diagram shows luminosity versus temperature, can also characterize absolute magnitude, relative size of the stars based on their luminosity, shown on the right side of the diagram. Now let's discuss stellar evolution. Stars form beginning when a shock wave from a nearby supernova compresses a nebula, and this causes a gravitational collapse within the nebula, where some regions of the nebula become dense enough for stars to form. As the matter continues to be squeezed or contracted in certain locations, temperatures increase in that nebula until they reach a threshold when nuclear fusions can begin and true stars are born. In a star, the inward pull of gravity balances the outward push of fusion. More than half of stars end up in a binary or two-star system. One example is that Sirius is a binary, though the B star is a very faint white dwarf that cannot be seen in the picture. We have on the right Sirius A, Sirius B, which orbits Sirius A. As the star evolves over its lifetime, its properties change, so its position on the HR diagram also changes. In the case of our Sun, we have the following evolution. The protostar is first forming at point 1 because of its large size, but cannot create fusion, and thus it is relatively cool. At stage 2, the newly formed protostar has a relatively high luminosity but still a low surface temperature. At stage 3, the protostar undergoes a contraction. Its surface temperature increases as its size and luminosity decrease. At stage 4, when fusion reactions begin, the luminosity and temperature both increase. And then at stage 5, a star arrives on the main sequence when a balance between outward pressure and inward gravitational pull come into equilibrium. This brings us to the question, how long does a star survive? Well, a star remains in equilibrium as long as hydrogen lasts in its core. More massive stars burn faster and live shorter lives even though they have more hydrogen, compared to the lowest mass stars, which are known as red dwarfs, which live the longest. None have yet left the main sequence because the universe hasn't existed long enough for red dwarfs to run out of hydrogen in their cores. It's important to know that all stars will become red giants or red supergiant stars towards the end of their evolution. After that, their final fate depends on the star's starting mass. A lower mass star, like our Sun, will eventually become a white dwarf. A nova is an explosion that occurs when a white dwarf steals mass from a companion in a binary system and then fuses it explosively. On the left, we have a nova in the same image sometime later. Here are the stages of nova development. When one star in a binary star gravitationally draws in the mass of its partner and eventually explodes. Novas may reoccur as the process then starts again with the white dwarf again stealing mass. Higher mass stars will produce supernova explosions. These occur when fusion occurs in shells throughout the star, and the star has eventually runs out of all fuel, collapses inward, and rebounds explosively. Supernovas release large amounts of energy and fuse other elements in the violent processes that occur. Any element larger than iron is produced in these explosions. One example is the M82 galaxy, which is 11 million light-years from Earth before and after a supernova. The supernova was visible in 2014. Neutron stars are tiny objects around 6 to 12 miles in diameter with a mass of 1.1 to 3 times the mass of our Sun. These are the remnants of the star that has gone supernova. One example is in the Crab Nebula, which has a neutron star as its center. Black holes are stellar remnants so dense that light cannot escape them. After a supernova, if enough mass is left, the object collapses down to an infinite mass with no actual diameter. The event horizon is the distance from the center at which gravity becomes so strong that even light can't escape. This is often considered the size of a black hole. Now let's put it all together in a summary to describe the life cycle of stars. Although stars all form in the same manner, their lives end differently depending on their mass. So we have two paths we can take: an average star or a massive star. Average stars become red giants, then planetary nebulas, then white dwarfs. Massive stars become super red giants, supernovas, and then they may either become neutron stars or black holes. The last section of our lecture will discuss galaxies and the structure of the universe. The Milky Way galaxy is our home galaxy and consists of 200 to 400 billion stars. It is about 100,000 light-years across. It contains a variety of galactic materials. Galaxies are classified by their visible structures. There are spiral galaxies, barred spiral galaxies, irregular galaxies, and elliptical galaxies. A quasar is an active galaxy that displays an extreme redshift, which means that it is one of the most distant objects detectable within the universe. This example shows a quasar 10 billion light-years from the Earth, as seen in an X-ray photograph from the Chandra Space Telescope. Galaxies can collide by interacting gravitationally and changing their structures. On the left is a picture of colliding galaxies known as the mice. On the right, we have interacting spiral galaxies. Andromeda is the nearest large galaxy to the Milky Way, which lies 2.5 million light-years from the Earth. It is the most distant object visible with the naked eye. The structure of the universe is best described as follows. Our local group is a group of 54 galaxies that includes the Milky Way and is about 10 million light-years across. A supercluster is a larger association containing hundreds of thousands of galaxies. One example is the Laniakea supercluster, containing several smaller clusters, including the local group. This supercluster is 500 million light-years across. On an even larger scale, the configuration of galaxies defines a three-dimensional mesh composed of string-like filaments and screen-like walls, whose dimensions are on the order of 30 to 300 million light-years. The last slide for this class briefly reminds us that the universe is expanding. Hubble's law is the speed at which distant galaxies are moving away from the Earth is proportional to their distance from the Earth. The singularity is the single point in space containing all matter and energy with an infinite temperature and density. And the Big Bang is the beginning of the universe upon the explosion and expansion of the singularity.